Hi, welcome back to recitation. We've been talking in lecture about antiderivatives. So I have here a problem for you, just an exercise about computing an antiderivative. So the question is to compute an antiderivative of this big fraction. So on top it's got x to the 8th plus 2x cubed minus x to the 2/3 minus 3, that whole thing over x squared. So just a quick linguistic note about why I said an antiderivative instead of the antiderivative, and then I'll let you work on it a little. So an antiderivative, there are many functions whose derivative is this function, right? So they all differ from each other by constants, so I would be happy with any one as an answer to this question. That's why I chose the word an antiderivative. So I'm looking for a function whose derivative is equal to this function. So why don't you take a couple minutes, work this out, come back, and you can check your answer against my work. OK, welcome back. So we were just talking about this antiderivative here. So one thing you'll notice about this function is that I've written this in a sort of silly form. And it's probably a lot easier to get a feel for what this function is if you break this fraction apart into its several pieces. So for example, x to the 8th over x squared is just x. So this antiderivative that I'm interested in, antiderivative of x to the 8th plus 2x cubed minus x to the 2/3 minus 3 over x squared dx. So I've written this in the silly form, and you can get it in a nicer form if you just realize that this is just a sum of powers of x that I've sort of put over this silly common denominator here. So OK, so our life will be a little simpler if we write this out by splitting it up into the separate fractions. So if I do that, this is just equal to the antiderivative of, well, x to the 8th over x squared. That's x to the 6th. And 2x cubed over x squared is just x. So I have x, it's 2x plus 2x. Now, OK, so x to the 2/3 over x squared. So that's x to the 2/3 minus 2, which is x to the minus 4/3. And minus 3 over x squared. So OK, so we could write that as minus 3 over x squared. Or maybe it's a little more convenient to write it as minus 3 x to the minus 2 dx. So far I haven't really done anything, a little bit of algebra here. OK, but now we know that we've seen a formula for anti-differentiating a single power of x. I mean, we know how to differentiate a single power of x, and so to do an antiderivative is just the inverse process. And we also know that when you have the derivative of a sum, it's the sum of derivatives. And so consequently, if you have the antiderivative of a sum, it's just the sum of the antiderivatives. So we can write this out into its constituent parts. So it's the antiderivative of x to the 6th dx plus the now, of course, you don't have to do this. You could probably proceed just from this step onwards, but I don't see any harm in actually splitting it up myself. So antiderivative of 2x dx minus, OK, x to the minus 4/3 dx plus minus 3x to the minus 2 dx. OK, so I just split it up into a bunch of pieces. Oh, I guess this one I sort of pulled the minus sign out, and this one I didn't. But whatever. It's either way. OK, so now we just need to remember our formulas for taking the antiderivative of a power of x. So in order to do that, so when you take a derivative, the power goes down by 1. So if you take an antiderivative, the power will always go up by 1. So in this case, you're going to get x to the 7th. And now when you differentiate x to the 7th, a 7 comes down in front, right? You get 7x to the 6th. So in order to get just x to the 6th, we have to also divide by that 7 there. So x to the 6th, the antiderivative is x to the 7th over 7, 2x. So that's going to give us plus 2x squared over 2. Or if you like, you could just recognize right away that 2x is the derivative of x squared. Minus, OK, now we've got minus powers, rather negative powers, so that always is a little trickier to keep track of. So again, the same thing is true, though. You add 1 to the exponent. The exponent goes up by 1 when you take an antiderivative. It goes down by 1 when you take a derivative. So OK, so when you add 1 to minus 4/3, you get minus 1/3. So we have x to the minus 1/3, and now I have to divide by minus 1/3. When I take a derivative here, we get of x to the minus 1/3, I get minus 1/3 x to the minus 4/3. So I need to divide by that minus 1/3. OK, and finally here, so minus 3x to the minus 2. So OK, so just like this first one, you might recognize that right off as the derivative of x to the minus 3. So this is plus. Oh, ha ha. You could do that if you were completely confused like me. So x to the minus 2, it increased by 1. Increases by 1. So when it increases by 1, you get minus 1, not minus 3. Oh, OK, good. So this is minus 3 times x to the minus 1 over minus 1. OK, that's much better. And if you like, right, so we could, any constant we add to this, it'll still be an antiderivative. OK, and now we could do a little bit of arithmetic to rearrange this into nicer forms if you wanted. So you could rewrite this as, say, x to the 7th over 7 plus x squared plus 3x to the minus 1/3 plus 3x to the minus 1 plus a constant. Now, suppose you got here, and suppose that you did the same mistake that I just made, and you had accidentally thought that this was going to be a minus 3rd power instead of a minus 1st power. So is there any way that you can prevent yourself making that mistake? Well, there actually is. So one nice thing about antiderivatives is that it's really easy to check your work. After you've computed an antiderivative, or something that you think is an antiderivative, you can always go back and take the derivative of the thing that you've computed and check that it's equal to what you started with. So if you're ever worried that you made a mistake computing an antiderivative, one thing you can always do is take a derivative of what you've got at the end. So if we take a derivative here, we get x to the 6th plus 2x minus x to the minus 4/3 minus 3x to the minus 2. OK? So that was just using our rule for powers one by one. And OK, so you say that out loud or write it down, and then you just check, right? So I said that. So that's exactly the same thing we've got right here. Yeah? So x to the 6th plus 2x minus x to the minus 4/3 minus 3x to the minus 2. So one of the nicest things about antiderivatives, they can be difficult to figure out in the first place. But after you've got something that you think is an antiderivative, it's very easy to go back and check whether you did it correctly by taking the derivative and making sure that it matches the thing that you were trying to antidifferentiate at the beginning. So that's that.